Welcome to Everything About Robotics Explained.
Imagine a robot navigating a busy factory floor or performing a delicate surgical task. It constantly relies on sensors like cameras and LiDAR to understand its surroundings. But what happens if a sensor glitches or a sudden, unexpected event throws off its data? How can the robot maintain its accuracy and continue its mission without skipping a beat? Robust filtering in robotics is fundamentally about enabling a robot to maintain an accurate understanding of its state and environment, even when faced with significant sensor noise, errors, or unexpected data outliers. It allows a robot to intelligently process imperfect information, ensuring reliable operation where precision and safety are paramount. The core mechanism behind robust filtering stems from the understanding that not all sensor measurements are equally trustworthy. Traditional filtering methods, like the widely used Kalman filter, assume that sensor noise follows a predictable Gaussian or normal distribution. However, in real-world robotic applications, sensors can provide sudden, large, and incorrect readings due to environmental disturbances, temporary occlusions, or sensor malfunctions. These are called outliers, and they can severely corrupt a robot's state estimate, leading to poor performance or even system failure. Robust filters are designed to mitigate the impact of such outliers, preventing them from disproportionately influencing the robot's belief about its own position, velocity, or the location of objects around it. To achieve this, robust filtering techniques often employ specific strategies to identify and downweight or outright reject data points that appear to be outliers. For instance, some methods use statistical tests to check if a measurement deviates too far from the expected range based on the robot's current estimate. Others might utilize adaptive weighting schemes where measurements that are less consistent with the overall data are given less importance in the state update. Algorithms like the Huber-M estimator or iterative reweighted least squares are common approaches that blend the benefits of traditional filters with outlier rejection capabilities. Additionally, some advanced filters, such as particle filters, inherently offer more robustness by representing the robot's state as a set of possibilities rather than a single estimate, making them less susceptible to single, erroneous measurements. A fascinating insight into this field is the concept of a chi-squared test for innovation. This statistical test is often used within robust filtering frameworks to evaluate the likelihood that a new sensor measurement, called an innovation, genuinely belongs to the expected distribution of errors. If the innovation is too large, exceeding a certain threshold, the filter can decide to either reject that measurement entirely or reduce its influence significantly. This selective processing of data is what gives robust filters their power to maintain reliable estimates under challenging conditions, moving beyond simple error correction to intelligent data discernment. It is a critical component for achieving fault-tolerant autonomy. Ultimately, the benefit of robust filtering is about building more resilient and dependable robotic systems. By systematically handling unpredictable sensor data, robots can operate more safely and effectively in complex, dynamic, and often uncertain real-world environments. This leads to higher accuracy, reduced risk of error, and greater confidence in autonomous operations, whether the robot is navigating urban landscapes, exploring remote planets, or assisting in critical human tasks. It empowers robots to make sound decisions even when their sensory input is far from perfect.
If you love robotics, like, subscribe, and keep building with us.